Hello, Principles of Biomedical Science students. We did 1.1.5 today, and today is Monday, October 12th, or if you're in my Block 1B, it was Friday, October 9th. So to get this done, the first thing you need to do is to log on to mypltw.org. So I'll give you a minute to do that. Pause this if you need to. All right, so you've logged on. Click from the main page, click Courses, and it brings you to your library. You see COVID-19 Pandemic and Principles of Biomedical Science. So you click Principles of Biomedical Science, as always. You see the two young ladies examining the skull. Use the left side search bar and go to Lesson 1.1, Investigating the Scene. We are on 1.1.5, so it starts at 1.1.1. Scroll down the left sidebar until you see 1.1.5, DNA Evidence. Here it is. This is where we are today. So explore the structure and properties of DNA. Examine how and why DNA is used in forensic science, and discuss what tests are used to analyze information in DNA. It's a lot to get done, so let's take a look. We're here and we need to have our lab journal entry open as well. So click back to your page and you click from Stream over to Classwork. Now, if you're an A-Day student, you'll find the 1.1.5 in Monday 10/12. If you are a B-Day student, you should find this in Friday 10/9. So wherever it is, just open it up, okay? So you're looking at this. And the first question you need to answer is, what charge does DNA have? If you scroll through, you see right here, DNA is a negatively charged molecule. So the answer to this first question, what charge does DNA have? The answer is negative. And if we look, you can see right here how G always pairs with C and A always pairs with T, something that I'm sure you remembered from biology. But if not, it's right here. And then scroll down a little bit more and you'll see definitions. There are lots of new vocabulary words, or at least vocabulary you probably haven't used in a while, so I'd like for you to define them. Almost all of these, with the exception of purine and pyrimidine, can be found as red text in your PLTW thing. And if you click on it, it pulls up a definition. So that's really super simple. My only thing is make sure you understand the definition, because if you don't, then it's useless. All right, so I will let you do that on your own, the definitions. Next, it says type the complementary strand of DNA for the given strand. You can always do this because you know A pairs with T and C pairs with G. So here you're given a strand ATCC TTAC GGCC TAAGGCC Now the complementary strand for that would be TAAC. If you could not keep up with that typing, I did put a copy of what we did together in today's topic. So if you need that, it would be in Monday 10/12 for my A-Day students and Friday 10-9 for my B-Day students. So how might DNA be useful in solving the mystery of Anna's death? Pause here and think about that. All right, so yes, some ideas that my classes that you have come up with is we can find out whose blood was at the scene. That was the most recent example. So next we have DNA profiling. So if you look at your page in my PLTW, scroll down to DNA profiling. And it's asking, can we find DNA in these things? So the first one, red blood cells. Flip the card. No, surprisingly, you cannot. Red blood cells don't have a nucleus. Okay, so that's the answer for this one. No, no nucleus. If you need these typed out for you, look at the completed work. Bone? Yes. DNA comes from the bone marrow. Hair? Yes, as long as the follicle is there. Preserved body parts? Yes, even from chemically preserved body parts. Clothing and fibers? Yes. DNA can come from cells left on clothing and fibers, even if it's been laundered or bleached. And finally, saliva and body fluids. You probably know the answer to this one, but let's flip the card anyway. Yes. Yes, as long as there are cells, there can be DNA. So you can click, or you can put yes, cells equal DNA. So what are some possible sources of DNA from Anna Garcia's scene? Pause it and think about it. The blood, that's right. The hair, yep. The beaker, the flask, maybe. Sure, all of these things and more. And the explanation, guys, is very simple. Where you find cells, you find DNA. Now, here is where we would do the extraction of our own DNA if we were in class. And you would see that humans have a very, very small amount of DNA, even in hundreds of cells. So the first thing a scientist would do, given a sample of cells, is make billions of copies of them. And that's called polymerase chain reaction, PCR. Make millions of copies of somebody's DNA. Then they dump in a restriction enzyme found in bacteria, which cuts DNA at recognition sites. And no two people's DNA gets cut exactly the same. So after you put the enzyme in and it cuts at restriction sites or recognition sites, you have a restriction digestion. That is somebody's DNA cut into a bunch of fragments of various lengths. And then you run it through gel electrophoresis and the fragments separate by size. Pretty cool. All right, so now we are going to use HALE to cut between GG and CC. Restriction enzymes. You have some examples here of EcoR1, HALE, and Hindi. EcoR1 and Hindi, they cut unevenly. That's called leaving sticky ends. The one we're going to use is HALE. It's a very common one, and it cuts straight down. It leaves a blunt end. When you have sticky ends like this, things are going to want to fill that in. But when you have a blunt end, it's fine. Nothing wants to fill it in because there's nothing left unpaired. So read the top strand, and where you find GGCC, that's where it cuts. only look at the top strand, but it does cut through both. So here's the first person number 1. I'm going to make spaces there where it cuts. It cuts between G and C when you see G, G, C, C. But here's another one, G, G, C, C. It cuts between the G and the C. But it cuts both strands. Just read the top strand. And here's another place, G, G, C, C. I'm going to cut it by making spaces. And you can see person number 1 has 1, 2, 3, 4 fragments of DNA. Person number 2, let's take a look. Here's a GGCC. It cuts there. And let's keep reading. Just the top strand. Here's CCGG, but that's not the same. Because remember, the top strand gets read from left to right like a book. So if that's not GGCC on the top strand, it's not going to cut. So that's all person 2 gets is 1, 2 fragments. So you can recognize person 1 from person 2 because person 1 has 4 fragments. Person 2 only has 2. All right, conclusion questions. DNA has 2 strands. If the sequence of nucleotides for one strand is known, can you figure out the second strand? Of course you can, yes. Because you know A always pairs with T and G always pairs with C. The second question, can you be framed by your own DNA? The answer, think about walking to a grocery store, walking through the grocery store and then leaving. Odds are very, 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 very good that you've left a few strands of hair in that store, that you've touched something. Maybe you weren't wearing a mask and you sneezed, so some of your DNA will be found there. Now, if a crime occurs later that same day, the detectives will find your DNA there. Could you be framed by it? Yes, you could. So if you leave cells somewhere and a crime is later committed, your DNA has framed you. All right, so now all you have to do, guys, is go through and do the definitions, part 1 and part 2, and then turn those into me, okay? Make sure you turn that in. All right.